Now, um, the way we start Lewis structures, and you should have already seen this in lab, but I'm going to go ahead and just do a quick recap. We start with Lewis symbols. A Lewis symbol is just the atom surrounded by however many valence electrons it has. This is really only useful for the main group elements, so S block and P block. So you can have, for example, sodium. We hop over to the periodic table, and we see sodium over here in the first column. It's an alkali metal. It only has one valence electron, so we represent that here in the Lewis symbol as boop. Just we draw a single electron. I recommend doing a circle or an X, something highly visible. Don't just do a dot. Those are really easy to lose. And then, of course, this can become an ion just by losing that single electron and becoming, sodium 1+. The square brackets are kind of overkill, but we definitely use those when we start drawing molecules. Meanwhile, we have something like carbon. We come over here to the periodic table. We see carbon. It's over here in the P block. It's in the second column of the P block. It has 4 valence electrons. So we can draw that either S, S, P, and P to show that those 2 S electrons are grouped together. And that is, technically correct, the best kind of correct. You can also draw it like this, with the 4 electrons separate. Less technically correct, but it does represent, it helps understand why carbon likes to form 4 bonds. It wants to get that stable octet. So this is what it will end up doing, as we'll understand when we start talking about hybrid orbitals. So either one of these is fine. Okay. Or we can get oxygen. Oxygen is 2 columns over from carbon. We see it over here. It is in the 4th column of the P block, so it has 4 P electrons. S, S, P, 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 P. And we see thus that when oxygen forms its ion, it will gain 2 electrons. It'll be oxygen, S, S, P, P, P. If it were to form an ion, it would do that by gaining an electron there and an electron there to become oxygen 2-. Let me shut the door real quick. Okay. So, that is how we draw Lewis symbols. We just surround it by the valence electrons. You can see how it would get a little bit tricky if you tried to do that with more than 8 electrons. It would just start to get real crowded. That's why we limit this to main group elements. We could technically do it for any if we were willing to just take it more space, make it more messy. Now, Lewis structures for molecules. Here are the rules for how we do Lewis structures for molecules. Okay, first, you add up your valence electrons. Okay, so you're going to count up all the valence electrons available from your molecule. Okay, you just look at the chemical formula, however many electrons are given by each of your atoms. And don't forget, you subtract the charge on the compound. So a neutral compound, this is because you get a charge by adding or removing electrons. A positive charge means you've removed electrons. A negative charge means you've added electrons. So subtract the charge, and that will change the total number of electrons available in the pool that you'll have available to work with. So, for example, we have, let's go ahead and work with, let's do ammonia. So, ammonia, NH3, okay. Again, from the periodic table, just valence electrons. Nitrogen has 5. There are 3 3 hydrogen atoms, each of which gives us 1. We have a total of 8 electrons. And that is the pool that we're going to work with to build up our total number, the bonds, the lone pairs, all that stuff, to give us our Lewis structure. So step 2. core atom goes in the middle. You surround it with satellite atoms. These are not at all official names. I just chose those because I needed something to call them. So you have one atom that goes in the middle. I call that the satellite. I call that the core, and then you surround it with the satellite atoms, the atoms on the outside, the ones that aren't in the middle. The core is usually going to be less electronegative, alone, and written first. All of these are just guidelines. They can all be broken. Okay. So, for example, we look at ammonia. Okay, the core atom is going to be nitrogen. There's only one of it, so that's true. It's alone, and it's written first, but it is not less electronegative. Nitrogen is more electronegative than hydrogen. We can also look at, for example, water. We look at water. Oxygen is going to go in the middle. It is alone. It is not less electronegative, and it is not written first. Okay. Then we come to, say, methane, CH4. Carbon is alone, and it's written first. Is it less electronegative? No, it's about the same electronegative. So these rules are just sort of guidelines. But being alone is a good rule of thumb. But even that can be broken, as we'll discover when I talk about formal charge. So in this case, we have ammonia. Nitrogen is going to be in the middle. We surround it with our hydrogen atoms. Okay, so there's our core, and the 3 hydrogen atoms are our satellites. So our third rule, or third step, these aren't really rules, they're steps. We're going to draw a single bond from the core to each satellite. Okay, so here we have nitrogen surrounded by our hydrogen atoms, and then we just draw a single bond. Remember, bonds are just lines, and each line represents a pair of electrons. So each bond removes 2 electrons from our pool. Okay. So we started with 8 electrons, and then we drew 3 bonds in here, so we lose 6 electrons. We have 2 electrons left over. Step 4, fill in the octet on each satellite by adding lone pairs. And again, lone pairs use up 2 electrons. Now, a lone pair is a pair of electrons that is just, it sits on the atom, it sits in the atomic orbitals of that atom, and it satisfies the octet. It is not engaged in bonding, not really. So they're also called non-bonding pairs or non-bonding electrons. Now, the thing about hydrogen is that hydrogen is one of the exceptions to the octet rule. Okay, there are others. So 2 exceptions to the octet rule where they don't necessarily fill up. Hydrogen always 2. Hydrogen never ever goes beyond 2. It is on the first energy level, so back to the periodic table. It's on the first energy level, and the first energy level only has the s sublevel, only has the 1 orbital. Hydrogen will only ever have 2 electrons. Thus, hydrogen will form bonds, a single bond, and that's it. So the octet is technically full already in this drawing. Okay. The other exception for an unfilled orbital is boron. Boron can stop at 6. Boron is on the second energy level. You can see it. It's element number 5 right here. So boron is happy to stop at 6 just because it's weird. It can go on to 8. It's happy to go on to 8, but it can stop at 6. So be aware that boron can have some oddities, and that is something that will definitely throw at you on the test. Boron. They will ask you to do a boron structure, and the fact that boron stops at 6 will play a role in that structure. So that's why the structure we have for this particular step are nitrogens surrounded by hydrogens, and then we have our single bonds inside that structure. We don't have to do anything on this step 4 because hydrogens don't take lone pairs ever. I mean, if it were a hydride ion floating around by itself, H1 minus, then that would be an exception, but hydrogen will form a bond, and that's it. Okay. All right, so that brings us to step 5. For step 5, any remaining electrons will go on the core atom as lone pairs. Okay. So in this case, we have 2 electrons left over in our pool. So we have nitrogen, our hydrogens around it, and then we have our 3 bonds. So we started with 8 electrons. We used up 6 of those electrons for our bonds, leaving us with 2. Now we're going to throw those electrons onto nitrogen as a lone pair. So that uses up those 2 electrons, leaving us with 0. So now step 6. Step 6, we check on the octet of the core atom. We've used up our pool of electrons, okay? So we're going to have to get a little bit creative if we need to fill in the octet, but all right. So if necessary, you fill in the octet of your core atom by turning satellite atom lone pairs from the satellite atoms. You turn those into double or triple bonds. In this case, that's not necessary because nitrogen already has an octet. It has 2 electrons from this bond, 2 electrons from this bond, 2 electrons from this bond, and 2 electrons from the lone pair. So it sees 8 electrons around itself. It's entirely happy, not a problem. Also, we couldn't form double bonds if we wanted to because the hydrogens don't have lone pairs. But there are some molecules where you need to turn lone pairs into double or triple bonds. Every time you do that, the number of electrons seen by the atom in the middle will go up by 2, thus making it happier. So, huzzah, hooray, happy day. Okay, now that's not necessary for this particular molecule, but it's necessary on some. And that should be enough to finish off the basic Lewis structure for any molecule. That said, there are ways to improve upon that, and that's what I'll talk about after we do some more practice with Lewis structures. That's what formal charges are for. But for now, let's just practice Lewis structures. So first up, let's go ahead, do another old favorite. Let's do carbon dioxide, CO2. Okay, carbon gives us 4. We have 2 oxygens giving us a total of 6, or giving us 6 each, so 12 plus 4, we have 16 electrons to play with. Carbon goes in the middle. In this case, carbon is written first. There's only one of it, and it's less electronegative, so it follows all 3 of those guidelines. And then we put the oxygens around it. Now we draw single bonds from carbon to oxygen. Each single bond uses up 2 electrons, so 2 bonds, 2 electrons each. We've used up 4, leaving us with 12 electrons. Now we go ahead and we fill in the octet on each of our oxygens by adding lone pairs. So this oxygen, it has 2 electrons already from this bond. So 2, 4, 6, 8. So whenever you fill in the octet, you're basically just adding 6 more electrons. So 2, 4, 6, 8, 10, 12. Okay. So now each of our oxygens is happy. We're completely out of electrons. So I say each of our oxygens is happy because each oxygen looks around itself. It sees 2, 4, 6, 8. 2, 4, 6, and then 8 from the bond. So each oxygen has a stable octet. Each oxygen is good to go. Meanwhile, carbon is not yet happy. It only has 2 electrons here, 2 electrons there, for a total of 4. Okay. The next step would have been to add to turn any remaining electrons into lone pairs, but we don't have any electrons left over. So the only way to satisfy carbon's octet is by turning lone pairs from the oxygens into double or triple bonds. So we have some options here because we have 2 oxygens, but these 2 oxygens are exactly the same. Okay, so there's no reason to choose this oxygen instead of that oxygen. On top of that, carbon needs 4 more electrons, so it's going to need 2 lone pairs to be turned into 2 more bonds. So we could do a triple bond over here and a single bond over there. Okay, we could turn 2 lone pairs from this oxygen into a triple bond. Well, 1 pair into a second bond, another lone pair into a third bond, and that would make carbon happy. 3 on one side, 1 on the other. A total of 4 bonds would be 8 electrons. But like I said, these 2 oxygens are exactly the same. There's no reason for this guy to have 3 bonds and this guy to have 1. So instead, what happens is we turn this lone pair into a double bond on this side, and this lone pair into a double bond on that side. Now, each oxygen still has 8 electrons. 2, 4, 6, 8. 2, 4, 6, 8. Okay. So each oxygen still has a stable octet. Turning lone pairs into double or triple bonds won't change the octet on the satellite. You do that too. But now carbon also has a stable octet. 2, 4, 6, 8. 4 bonds, 8 electrons. Okay. So this is carbon dioxide. You can clean it up a little bit. O, C, O. Lone pair, lone pair, lone pair, lone pair. And you can see why I recommend drawing circles rather than doing dots, because those dots are probably not highly visible in the YouTube video, especially not if there's any buffering or if you can't get it at a great resolution. So that's why circle, 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 circle is a lot better than just doing dots. Okay. So that is carbon dioxide. Now, let's go ahead and explore another exception to the octet rule by doing iodine pentafluoride. So, iodine pentafluoride, IF5. Okay. Iodine gives us 7. There are 5 fluorines giving us 7 each. So we have a total of 42 electrons. Iodine is going to go at the middle. Then we have fluorine, 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 and fluorine. So there are 5 fluorines. We draw a single bond to each of these fluorines. 1, 2, 3, 4, 5. 5 bonds, 2 electrons each. That uses up 10 of our electrons. We have 32 left. Now we fill in the octets on our fluorines by adding lone pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So filling in the octets uses up 30 of our remaining electrons. We have 2 left over. Those 2 electrons will now go on iodine, as a lone pair in order to use them up. So 2 more electrons, we're down to 0. So all of our fluorines have a stable octet. Is our iodine happy? Do we need to make any double bonds? Well, how many does iodine have? 2, 4, 6, 8, 10 from the bonds, and then 2 more from the non-bonding pair or the lone pair gives us a total of 12. So iodine has 12 electrons. And yeah, that's fine. That is another exception, okay, to the octet rule. It is called the expanded octets. Essentially, any element from the 3rd row of the periodic table or below can go beyond 8 electrons. Perfectly capable of doing that, because once you get to the 3rd row, you have a D subshell available that's empty. Okay, so phosphorus, it has, you know, its valence electrons go into the P subshell, but then it has this empty D subshell available that you can put electrons into, and so it can keep on forming bonds. So anything from the 3rd row or below. But the 2nd row can't do that, because the D subshell isn't available until you get to the 3rd energy level. Okay. So that's an expanded octet, not a problem. But 2nd row, it has to stop at 8. Absolutely. No exception. Has to stop at 8. That's a hard and fast. Likewise, hydrogen stops at 2. Okay. So that is your other exception to the octet rule. Now let's go ahead and show some with charges. Let's look at charges. Or sorry, charged molecules. Let's do another really popular compound. Let's look at ammonium. Notice ammonium, not ammonia. Ammonia is NH3. Ammonium is NH4 1+. Okay. So once again, nitrogen gives us 5 valence electrons. We have 4 hydrogens, each of which gives us 1. So we're adding 4. But then we have a positive 1 charge. So we subtract 1 for that, because that positive 1 charge means we've lost 1 electron somewhere. So 5 plus 4 is 9 minus 1. We have 8 electrons. So nitrogen, once again, goes in the middle. We surround it with our hydrogens. Then we draw a single bond to each of our hydrogens. And that uses up the last of our electrons. No need to worry about filling in the octets. Hydrogen stops at 2. Nitrogen, likewise, we don't need to worry about double bonds or anything, because it has 2, 4, 6, 8. 4 bonds, 8 electrons, so it's also happy. So the only thing left to do is to show that this is an ion by putting brackets around it and indicating that the whole thing has a positive charge. And that is ammonium. Okay. Don't forget the brackets and the charge, otherwise you are wrong, and you'll lose points, and your parents will not be proud of you, and they won't love you anymore. Now let's look at a negative molecule. Let us look at carbonate, CO3 2-. Another really popular guy. He shows up in baking soda. You can find him in a lot of rocks. Calcium carbonate is limestone, and it's also the hard shell of tiny little sea creatures. So that's fun. It's fun in a lot of different ways. So carbonate. Carbon gives us 4. We have 3 oxygens, each of whom gives us 6 electrons. And then we have a -2 charge, so we subtract -2. Basically, subtracting -2 is the same as adding 2. We have 2 extra electrons from somewhere. 4 plus 18 is 22, plus 2 is 24 electrons. Carbon is going to go in the middle. Then we put oxygens around it. That is the basic. Okay, so now let's go ahead and add our single bonds. Boop, boop, boop. 3 bonds means 6 electrons, leaving us with 18 to play with. Now we fill in the octet on each of our electrons using lone pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, so filling in the octets there uses up all of our electrons. We have 0 electrons left, which means no lone pairs on carbon. Unfortunately, carbon is not yet satisfied. Carbon only has 1, 2, 3 bonds for a total of 6 electrons. So we are going to have to come in and turn a lone pair into a double bond. And now carbon is happy. And with that, we go ahead and we put the box around it and say it has a -2 charge. And that is carbonate. Now, another reason that I chose this guy is because he is instructive of another really important thing, namely resonance. You might have already heard this term when I talked about degeneracy. I may have brought it up, I can't recall. But in this case, it has to do with the location of the double bond. There is absolutely no reason for the double bond to be here instead of here. Or here. These oxygen atoms are all the same. They have the same valence, the same electrons. They're absolutely identical. There's no reason to put it in this place rather than this place. Therefore, we don't put it in this place rather than this place. Okay? It is here, and it's here, and it's here. Okay? When we look at the carbonate molecule, using the various methods at our available, we can actually study these bonds. And when we do that, we do not see 2 single bonds and a double bond. Instead, what we see is 3 completely identical bonds, all of them partly in between a single bond and a double bond. So resonance means that this bond exists in all 3 locations at the same time. Remember when I talked about electrons at some point, when an electron, if you walk into a room and you see 5 empty chairs, you sit in one of the chairs and that's it. When an electron walks into a room, if it sees 5 empty chairs, it'll sit in all 5 chairs at the same time because that's how they roll. That's resonance. So this bond, it doesn't just exist here. It exists in all 3 locations. But it's not bouncing around from one to the other. It doesn't exist here, sometimes there, sometimes no. Instead, it exists in all 3 locations simultaneously. This is one of the things about quantum mechanics that's just plain weird. Okay? Subatomic particles, electrons, these things, they can do things that stuff in the everyday world just can't do. Okay? They're just different. So we have to indicate that this bond exists in all 3 locations at the same time. And the way we do that is by, drawing 3 pictures. So let me sketch this out real quick. Okay, we have carbon, oxygen, 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 single, double, single. Carbon, oxygen, 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 single, double, single. Carbon, oxygen, 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 single, single, double. And these all have lone pairs, which are going to be largely invisible to you guys because I'm just doing dots to save myself a little bit of time, but trust me, they are there. I'm not forgetting them. You can see me adding them even if you can't necessarily see them. And then we put brackets on each of these to show they have a 2- charge. And then we draw these double-headed arrows to show that these are what we call resonance structures, to show that all 3 of these pictures are equally true at the same time. The only way to actually represent the carbonate compound is to draw all 3 of these structures. Okay. Some resonance structures have 2 structures, some have 3. You can get a lot. I think there's one I can think of that I think has 12. No, 6. Sorry. I forgot. Anyway, but they can be a lot, is the point I'm trying to make. Okay. So look out for resonance. Now, the thing about resonance is that it can only happen if you have double or triple bonds. Later on, when we talk about single bonds and pi bonds, when we talk about hybridization, you can start to understand why that is. But if all you have is single bonds, you don't have to worry about resonance. You can only get resonance if you have multiple bonds. So when you see a multiple bond, a double bond or a triple bond, just take a look at the molecule and ask, can this go in multiple locations? Because if it can, you might have resonance. Okay, so just keep an eye out for that. If you have perfectly identical locations where it could go, you definitely have resonance. And thus, the only way to fully draw the molecule, to fully represent it, you have to draw your resonance structures. All right. Now let's talk about formal charges. Okay. Formal charge is a tool to analyze a Lewis structure to see how good it is. Okay, so formal charge, it is not an actual charge. It doesn't necessarily represent anything real about the molecule. Okay? Instead, it is a tool we use to analyze a Lewis structure, and if necessary, correct it to make it better. Okay? So what you do is you find the formal charge for each atom. You can't do it for the molecule as a whole. It has to be for every individual atom. And then once you do that, you analyze the formal charge. Okay. 0 is the best. You want the lowest possible formal charge. 1 or -1 is okay. 2 or -2 is bad. The further you get from 0, the worse it is. Okay, you want lower numbers, with 0 being the best. Next up, you want your negative formal charge on the more electronegative elements. So if you have to choose between having a -1 on carbon versus a -1 on oxygen, put the -1 on oxygen because oxygen is a more electronegative element. Okay. And finally, don't put like charges on adjacent atoms. You don't want positive charges next to each other. You don't want negative charges next to each other. That's just bad. Okay. So how do you calculate formal charge? Okay. Formal charge, there are a couple of different ways of looking at it. So the formal charge is equal to the number of valence electrons in the neutral atom minus the number of electrons owned by the atom once it has its bonds. Number of electrons owned by the atom if you have a lone pair on the atom, it's not sharing those electrons, so it owns both of the electrons in a lone pair or non-bonding pair. If you're looking at a bond, though, there are 2 electrons in the bond, but it has to share those electrons with the atom on the other end of the bond. So you only get 1 electron per bond. So if you're watching the lecture videos put up by Shelby Duffy, trying the school, then they would tell you that it is a number of valence minus 1 times the number of bonds minus 2 times the number of lone pairs. So what you'll end up with is 3 numbers under each atom. That works just fine. I just count the number of electrons on each thing by counting each electron in the lone pair, and then I count the number of bonds. However you do it, so long as you consistently get the right answer, that's what really matters. Okay? So once we have the formal charges, and you have to find the formal charge of every single atom, then you use these guidelines to judge the structure and see how good your structure is. Oh, one last thing. When you add up all your formal charges, they will add up to the total charge on your compound. CMPD is my abbreviation for compound. A molecule, in this case, chemical compound. So if you have a neutral atom, then you add up all the formal charges, they should add up to 0. On carbonate has a 2- charge, so you add up all your formal charges, they'll add up to -2. This is just a quick check to make sure you haven't done anything wrong. If you get if you add up your formal charges, you get a different number. It means either you calculated one or more of your formal charges wrong, or you really screwed up on the Lewis structure. So that is just a quick way to check yourself before you figuratively wreck yourself. Okay. So let's go ahead and use formal charges to judge a couple of compounds. Okay. So first up, CO2. CO2, really quick, we've already done this one, is this guy right here. Carbon double bonded to 2 oxygens. Each of our oxygens has 2 lone pairs. Okay. So oxygen started with 6 valence electrons. Carbon started with 4. Okay. So this oxygen, he looks around himself and he sees 1, 2, 3, 4, 5, 6 electrons. Okay, those are all the electrons he owns in this molecule. 2 for each lone pair, 1 for each bond. Meaning this oxygen over here has a 0 formal charge. So does this guy. 2 lone pairs, 2 bonds. He owns a total of 6 electrons for formal charge of 0. Meanwhile, our carbon here in the middle, he looks around himself. 1, 2, 3, 4. 1 for each bond, meaning he owns, here, bunny ears, owns 4 electrons in this molecule. He also has a formal charge of 0. So 0 plus 0 plus 0 equals 0. CO2 has a 0 charge, so this is good. This explains valence. The old version of valence. Remember when they started coming up with the periodic table and they were looking at shapes, they were trying to find patterns, they arranged things not just by weight, but by valence, back when valence meant how many atoms does each thing like to bond with. Oxygen had a valence of 2, nitrogen had a valence of 3, carbon had a valence of 4. And we see this with formal charge. Oxygen likes to form 2 bonds, because he has 2 slots open in his P subshell. So making 2 bonds fills out his octet and makes him happy. Meanwhile, carbon has 4 slots open, so he likes to form 4 bonds. Okay. What you'll see over and over again in Lewis structures, that the happiest structures typically, not always, but typically have oxygen with 2 bonds, carbon with 4 bonds, nitrogen with 3 bonds. Your halogens only have 1 bond, and so on. There will always be exceptions, okay? Always. But that is a good rule of thumb, a good way to, something to keep in mind, just as a helpful guideline. Okay? Going back to the structures I was talking about at the end of the first half of Chapter 4, carbon likes to form 4 bonds. That's what makes it really, really versatile in organic chemistry. It can form big, complex branching structures because it can form bonds in all directions. Whereas oxygen would be very, very limited if it tried to fill that role because it can only form 2 bonds. It can only make a single chain. It can't branch. All right, so that's carbon dioxide. Let's look at carbonate, CO3 2-. CO3 2-. I'll only draw one of the pictures because we don't need to analyze every picture independently. They'll give us similar results. Let's We have to include the valence electrons, and I might as well make it so that you can see them. Okay. All right. So carbon, once again, started with 4 valence electrons, always. And we look at carbon, it sees 1, 2, 3, 4 bonds. Each bond only gives it 1 electron, so it owns 4 electrons, giving it a formal charge of 0. Now this oxygen, up here, it looks around it and started with 6. It looks around itself, it sees 2 and 4 from the lone pairs, and then 1 and 1 from each of the bonds, so 2, 4, 6 valence electrons around itself, giving it a formal charge of 0. The 2 oxygens down here are different. This oxygen, they each again started with 6, but 1, 2, 3, 4, 5, 6 from the lone pairs, and then 1 more from the bond, means that each of these oxygen owns 7 electrons, giving it a formal charge of -1. Now, this is the best we can do. Okay? A 0 formal charge would be better, but there's nothing we can do to fix this structure. We'll talk about how you can fix structures in a minute, but this is the best we can do because it's going to have a -2 formal charge no matter what. Anything we could do would just move the -1 formal charge from oxygen onto carbon. Oxygen has the -1 formal charge, and that's okay, because oxygen is the more electronegative element. You want the more electronegative element to have the more negative formal charge. Okay? So carbon is 0, oxygen is -1. That's really the best you can do. So now let's look at a structure that we can fix. Let's look at phosphite. Okay. So phosphite, another polyatomic molecule, or polyatomic ion, is PO3 3-. Phosphorus gives us 5. We have 3 oxygens giving us 6 each. And then we have a -3 charge. So 5 plus 18 is 23, plus 3 means we have a total of 26 electrons. So phosphorus goes at the middle. Okay. Then we have oxygen, oxygen, oxygen. Single bond, single bond, single bond. So we lose 6, leaving us with 20 electrons. Then we fill in the lone pair on each of our oxygens. 2, 4, 6, 8, 10, 12, 14, 16, 18, leaving us with 2 electrons, which means that phosphorus gets a lone pair. Okay, now that I'm looking at this, I realize that this structure isn't going to need to be fixed. But I do know one that will need to be fixed, so we'll get to that in a minute. So this guy has a -3 charge. All right. The reason I'm saying it, well, we'll see this in a minute, but each of these oxygens started with 6. Each of these oxygens owns 7. 1, 2, 3, 4, 5, 6, 7. So each of our oxygens has a -1 formal charge. Meanwhile, our phosphorus started with 5. How many does it own? 1, 2, 3 from the bonds, 4 and 5 from the lone pair. So it has a formal charge of 0. Once again, our formal charges add up to -3. 0, -1, -1, -1, -3. And again, this is the best we can do. I chose poorly when it came to an example that would need to be fixed. So let's look at phosphate. Phosphate might need to be fixed. PO4 3-. Phosphate is a more popular molecule anyway. Should have started with him. So 5, 4 times 6, minus -3, 24, 29, 32 electrons. Phosphorus, oxygen, 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 oxygen. Bond, 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 bond. No, Mr. Bond, I expect you to die. 24 electrons left over. Let's get some lone pairs on here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that uses up all of our electrons. No lone pairs for phosphorus. And according to Lewis structure rules, he doesn't need lone pairs. He's got 4 bonds, 2 electrons per bond, means that the phosphorus has a stable octet. So we just go ahead, we draw our brackets, give it the -3 charge, and we're done. But I want to show you something. I will draw it quick, small, simple. This is phosphoric acid. The formula for phosphoric acid is H3PO4. And when we actually look at the structure of phosphoric acid, this is what we see. The hydrogens bond to 3 of the 4 oxygens, and then we have a double bond between phosphorus and the remaining oxygen. There is no reason for the double bond to just sort of spontaneously appear. Okay. We use formal charges, and we can see why this Lewis structure is not actually correct. This is what the Lewis structure rules get you, but formal charges tell you why it's not good enough. Okay? Formal structure rules mean that each of our oxygens, they started with 6, they own 7, 1, 2, 3, 4, 5, 6, 7. Each of our oxygens is going to have a -1 formal charge. And phosphorus started with 5. It only has 4 bonds, so 1 electron per bond means -4 gives it +1. Now, 1 minus 1 minus 1 minus 1 minus 1 still adds up to -3. So our formal charges add up to the charge on the molecule, not a problem. But here's the thing. We can improve on this structure in order to change 2 of these numbers into zeros. And remember, 0 is the best for formal charge. So what we do there is we turn a lone pair on one of the oxygens into a double bond. That's what we see down here. And when we do that, boom, boom, that's going to change the formal charge on this oxygen and on phosphorus. Okay? So this formal charge is no longer -1. Now it's 6 minus 6 equals 0. Because this oxygen with a double bond instead of a single bond, it owns 1, 2, 3, 4 from its 2 lone pairs, and then 5, 6 from its 2 bonds. And phosphorus also changes. Phosphorus still started with 5, but now it looks around itself, it sees 5 bonds, and thus 1, 2, 3, 4, 5 electrons. So now it too has a 0 formal charge. So that is how you can use formal charge to improve a Lewis structure. Okay? If you turn a lone pair into a double bond, it will decrease the formal charge of one atom and increase the formal charge of the other. Because you own both electrons in a lone pair, you only own 1 electron in a bond. So by turning a lone pair into a bond, you decrease the formal charge, you increase the formal charge, technically, of that atom. And since this guy gets an additional bond, it gets an additional electron, and its formal charge goes down by 1, because it owns 1 more electron. Okay? And thus, we can see why phosphate goes from this to this for phosphoric acid, because the hydrogens are bound to those oxygens, and that is the oxygen with a double bond. Now, of course, this also means that phosphate technically has a resonance structure. In order to fully represent it, we need 4 pictures, 1 with the double bond on each of these oxygens, because again, there's no particular reason why a double bond would be on this oxygen rather than one of these 3. So in order to fully represent it, you would need this picture and 1 with the double bond on the bottom, 1 with the double bond on the right, and 1 with the double bond on top. But I'm not actually going to draw that because I don't really have room on the page and I don't want to. Right. So that is how we can use formal charge to correct a structure. Now, let's use formal charge to judge structures. Okay? Let's look at dinitrogen monoxide, N2O. This is another really popular guide to use for formal charges because we don't know, just by looking at it, which of these is in the middle. Is it a nitrogen in the middle, or is the oxygen in the middle? It is difficult to tell. So what we do is we draw the Lewis structure either way. So let's start with nitrogen in the middle. We have a total of 16 electrons to play with. 2 times 5 plus 1 times 6 equals 16. Nitrogen in the middle with a nitrogen on one side, oxygen on the other. Then we draw a single bond to either side. That uses up 4 of our electrons, so minus 4 leaves us with 12. Now we add our lone pairs on the satellites, so 2, 4, 6, 8, 10, 12. So that uses up all our remaining electrons. The nitrogen in the middle doesn't yet have a stable octet. So the only way to remedy that is by bringing lone pairs in as double and triple bonds. But notice that these guys are no longer the same. So we can't just say, oh, well, it's going to be 2 double bonds, because the elements are different. Okay? So we have 3 possible structures coming out of just this one arrangement. One possible structure is nitrogen triple bond to oxygen with a single lone pair, single bond to nitrogen with 3 lone pairs. Another is nitrogen double bound to each of those guys, with each of them having 2 lone pairs. Or we can have the triple bond on the other side, triple bond to nitrogen, single bond to oxygen. So oxygen has 3 lone pairs, and this nitrogen has a single lone pair. So we have 3 possible structures just by having nitrogen in the middle. But we also have to consider, is oxygen in the middle? Instead of ONN, is it NON? So how many structures do we get out of that to compare? Well, we put oxygen in the middle, nitrogen on either side, and we're starting still with 16 electrons. We draw our single bond to either side. That uses up 4, and we have 12. Then we draw our lone pairs, 2, 4, 6, 8, 10, 12. And that uses up all of our electrons. Oxygen still isn't happy. And now we are going to end up with 2 possible structures. One of them is probably better than the other, just by the way, these things work, but we're going to be thorough. One is nitrogen, triple bond, oxygen, single bond, nitrogen. 1 lone pair here, 3 lone pairs here. The other one is with a double bond to either side. Okay. We don't need to do a triple bond on the other side, because if we did nitrogen, single bond, triple bond, nitrogen, that would just be this molecule flipped over. So we have 2 possible structures with oxygen in the middle. So that means we have 5 structures to analyze, and no obvious way to tell which one is best. That's what we're going to use the formal charges for. So I'm going to put them all on a single page, and then we'll compare them all side by side. So N triple bond, N single bond, O. N double bond, N double bond, O. N single bond, N triple bond, O. N triple bond, O single bond, N fill in all these lone pairs. Finally, N double bond O double bond N. Whew. All right. So regardless, nitrogen always started with 5 electrons, 5 valence electrons. Oxygen always started with 6. So it's going to be 5 minus something, 5 minus something, 6 minus something, 5, 5, 6, 5, 5, 6, 5, 6, 5, 5, 6, 5. All right. So how many electrons does each atom own in the molecule? Well, the atom in the middle is always going to own 4 electrons, regardless. Why? Because the atom in the middle always has 4 bonds. Each bond gives it 1 electron. So the atom in the middle, you're always going to be subtracting 4. For this set of molecules. For another set of molecules, it might be different. So I'm just trying to get through this a little bit more quickly. But 5 minus 4 is positive 1. 5 minus 4 is positive 1. 5 minus 4 is positive 1. 6 minus 4 is positive 2. 6 minus 4 is positive 2. All right. Now the atoms on either side. Okay. If it has a triple bond, then it owns 5 electrons because 1, 2, 3 from the bonds, and then 2 more from the lone pair. If it has a single bond, it owns 7 because 2, 4, 6 from the lone pairs, and then 1 more from the bond. If it has a double bond, it owns 6. 2, 4, 5, and 6. So triple bond, this oxygen or this nitrogen owns 5, giving it 0. Single bond, this oxygen owns 7, meaning -1. Double bond, it owns 6 for a total of -1. This guy owns 6 for a total of 0. Single bond, he owns 7 for -2. Single bond, he owns 5 for +1. 5 minus, he has a triple bond, so that's 5, so he has 0. This guy owns 7 for -2. Double bond is 6, double bond is 6. Each of these guys is -1. Now you can see that these are all good Lewis structures. I mean, good just as Lewis structures, because the formal charges all add up to 0. The charge on dinitrogen monoxide is 0. 0 plus 1 minus 1, -1 plus 1 plus 0, -2 plus 1 plus 1, 0 plus 2 minus 2, -1 plus 2, -1. They're all adding up to 0. So that's good. No mistakes. But some of these are better than others in terms of formal charge. So, going back, who knows how many pages? Yes, okay. So 0 is best. Negative on the more electronegative element. Don't put like charges on adjacent atoms. Well, none of these have like charges on adjacent atoms. You'll have a negative next to a positive, negative next to positive, negative next to positive, positive next to 0. That's fine. We didn't screw that up. 0 is the best, but the negative on the more electronegative element. Okay. So we want our formal charge to be as low as possible. So we're just going to go ahead. I'll use my brown marker because these things are crap. Anything with a 2 is going to be worse than something with just 1s. So this one is bad. This one is bad. And this one is complete garbage because they have 2s. Those are just worse. You want lower formal charges. Okay. This one is particularly bad because it has a +2 and a -2. This, no, absolutely not. All right, so now it comes down to this guy versus this guy. Is it nitrogen triple bound to nitrogen, single bound to oxygen? Or is it nitrogen with a double bond to nitrogen and a double bond to oxygen? Well, that's where the other rule comes in. We want the negative formal charge on the more electronegative element. And remember the rule for electronegatiivity, the highest electronegativities are over here in the upper right-hand corner. So fluorine has the highest electronegativity. Second highest is oxygen. Take another step to the left, nitrogen has a lower electronegativity. So oxygen, higher electronegativity, nitrogen lower. So oxygen should have the negative formal charge, meaning that this guy right here is the best Lewis structure. Negative charge on the more electronegative element. All right. So that is what formal charge is good for. Okay, it lets us improve on structures like we did with phosphate to show that there is actually resonance. It has a single double bond on all four of those oxygens. And it also tells us that this is the better structure than this. Dinitrogen monoxide has a nitrogen in the middle with a triple bond to the other nitrogen, a single bond over to the oxygen. Now, that said, that is almost certainly, if they gave this to you on a test, this is where they would stop, and they would ask you just to find the best Lewis structure using formal charges. You would have to draw out these 5, find the formal charges on all the atoms, discard these 3 because they have 2's in them, then discard, and then choose this one because it puts the -1 on the oxygen. Okay, that's where they would ask you to stop. But the fact is that this molecule probably has resonance. Both of these structures contribute. Now, the thing is, with something like carbonate, where you have a double bond existing between perfectly identical oxygens, carbonate, those 3 resonance structures exist equally. They're all equally true. But for this molecule, they wouldn't be equally true. I mean, if this contributes at all, it's going to be less than this one. It's sort of like the electron walks into the room and sits in the 5 chairs at the same time. Well, what if one of the chairs is really comfy and one of the chairs is really uncomfortable? Okay, so say you had a really great chair and then 3 mediocre chairs and then 1 really, really crappy chair, right? Well, the electron is going to spend most of its time here. It's going to spend some time in these 3 chairs, and then it's not going to be over here very much. Okay, that is something you can get with resonance. Okay, you can get distribution across different locations with unequal presence in each one, or unequal contribution from each one. Okay, so the electron is mostly over here, partly over here, and only a little bit over here. Right? In this case, the full picture of dinitrogen monoxide is probably a combination of these 2 pictures, mostly this one, a little bit this one. Okay, that's just kind of a guess based on the fact that I know that electrons like to spread out. They like to share. Oxygen doesn't really want this -1 formal charge. It would like to look like this. But nitrogen also wants a 0 formal charge. It doesn't want that negative formal charge. Okay. Oxygen is better at having the negative formal charge because it's the more electronegative element. So this picture contributes more to the total picture than this one. This picture contributes less to the total picture. So if you had resonance, it would be like, maybe 80% this, 20% that. Okay. Hard to say. You would have to, actually measure it. I don't think there's any way even to really make just an a priori prediction from that. All right. So those are Lewis structures and formal charges, how we do them and how we use them. Definitely, absolutely practice both of these. I mean, if nothing else, they're going to be vital. You need them to pass the next test. No question about it. You need them to pass the lab test. No question about that. And they're super important for the rest of the semester. You need to be able to get the correct Lewis structure in order to get the correct molecular geometry, in order to get the correct polarity, and thus know how the molecules are going to interact and all that sort of stuff. This is all really important. This is just incredibly fundamental basic chemistry that you need to build on for the rest of chemistry stuff to make sense. All right, and with that, I am talked out for the night. I've been doing this for a while, so I'm going to go ahead and I'm going to call it. I'll be doing more lab stuff in later videos, but that's it for the lecture videos this week. I will see you around.